So before we can jump into any code, right, with this idea of optimizing for correctness, we have to kind of set some rules up on what that means. And I briefly talked about words like integrity, readability, and simplicity. And I want to dive a little bit deeper into what these words mean, at least for Go, right? Some of these are buzzwords, and they can mean different things for different languages. So let's define what they mean for Go. And this is going to help us as we journey through our understanding of being about how to read code. So integrity is about becoming very serious about reliability. And there's two driving factors behind integrity. There's a micro level and a macro level. But before we could talk about that, let's think about any piece of code you've ever written before. Think about any piece of code you've ever written. It really only does three things. It allocates some memory, it reads that memory, and then it writes to that memory, right? This is what we're doing all day. This is what our code is doing all day. It's reading and writing to memory and allocating it when necessary. And if we want to take it to another level, all you're really doing is reading and writing integers all day. I mean, if you're doing some machine learning AI stuff on GPUs, then you're reading and writing floating points all day. But you know, this machine that I have right here, like the processor's integer based, right? Like, and this is why it's going to be so important to be, you know, when we start talking about integers and things, that you know, using the right integer is always going to be important, because this is a machine that's reading and writing integers all day long, right? And weird things happen. You're seeing me on your computer, and lights are flashing, and phones are buzzing, all because of that. At a micro level, what integrity means is that every one of those reads and every one of those writes that we're doing is accurate, consistent, and efficient. When we lose any of those three things, then we have an integrity issue. And unfortunately, when you have an integrity issue, if you can't recover, you've got to shut that software down. We all have stories of when a piece of software went rogue, integrity issues, and started corrupting things. There's also a macro level of integrity. And the idea of macro level integrity is the idea that every problem that we solve is a data problem. It's a data transformation problem. I call Go a data-oriented designed language, not object-oriented, but data-oriented. I'm going to show you that. And if you think about it, any problem you've ever solved is a data transformation problem. You get some data that comes in, we transform it, and it goes out. However it goes out is one way or the other. But this is what we're doing all day. And so the whole idea of data-oriented design is that if you don't understand the data, you do not understand the problem. And if you don't understand the problem, how can you write a single line of code to solve this problem? You can't. You know, we're all data scientists at the end of the day, regardless of whether we use formal machine learning models or not. We're all data scientists at the end of the day, and we gotta get that in our head. So at a macro level, what integrity means is that every function we write, right, which is in essence a data transformation, every data transformation we write also has to be accurate, consistent, and efficient. And if it's not, we've got integrity issues. So we've got to talk about things at a line of code in terms of readability. Eventually, we've got to talk about things at a function level around readability, because they both play into this idea of integrity. And I need you to put integrity first. Nothing can trump integrity. We see a piece of code that doesn't have integrity. You know, that code review, it has to stop. We've got to fix it. Now, at a macro level, there's two things that we can kind of focus on early on in a code base around integrity. One is writing less code. Here comes lines of code again coming in, right? And the other is really handling errors, because we're not worried about a program that is running perfectly when life is good. You know, as engineers, we have to worry about when life is bad. Let's talk about writing less code for 1 second. You know, there was a study done that analyzed code, and the study came up with the idea that for every 1,000 lines of code written, the average developer will produce anywhere from 15 to 50 bugs per 1,000 lines of code. So if we put ourselves in the bad developer bucket, which I want us all to do at all times, that basically means is that for every 20 lines of code that we write, put this in your head, for every 20 lines of code that you write, there's a bug introduced into your software, whether you like it or not. All right? Whether it shows itself or not, it doesn't matter. It's there. So how can we add less bugs to our code? You write less code, right? Here it is, that lines of code again. Again, what is Go trying to do with this language? It is trying to minimize the amount of code we need to solve problems. Again, a part of that is so there's less bugs introduced in the code. I mean, just do the math, right? And There's other ideas here also that you only should have the code you need for that version of that product. Having more code than you need also causes problems. It leaves places for bugs to hide. It also starts to create situations where you have incomplete tests because you start not writing the tests you need because you've got all this extra code and you don't have time, right? And then eventually what happens is, as well, is you start walking away from your patterns and your frameworks and you start to hack code. All of these things happen when you're not maintaining a mental model of your code base. You're not revising or refactoring that code base. When you're not constantly in this idea that let's just have the minimal amount of code we need at any given time for any given version, and we'll keep that code clean. So all of these things are going to help with integrity, and it's something you're going to be doing day in and day out. I always tell people that if you worked for an entire day with me, you're probably going to spend 30% of your time writing new code and 70% of your time refactoring that code towards readability, integrity, and mental models. Now, on the error handling side, a lot of people don't like the tediousness of error handling. But I always say that there are certain things that need to be tedious. Security needs to be tedious, right? And I turned two-factor authorization, right? As it was called, two-factor, off my phone because it was so tedious to get into my phone. I couldn't take it anymore. I was like, I'd rather be less secure, right? Like, the best security systems are tedious. Well, guess what? The bulk of what we do as engineers is about failure. It's not about success. And so your error handling needs to be a little tedious because we've got to constantly be thinking about what happens here if it fails, what happens here if it fails. So I don't have a problem with Go's error handling mechanics. I really don't. I know that they're looking at, for a Go 2.0, a way of maybe making it a little less tedious. But I start to think about, are we optimizing for laziness now instead of optimizing for correctness? These things kind of scare me. But there was a study done where 48 critical failures that caused this software to kind of crash and burn were looked at. One of them is Redis. I mean, think about how much Redis is used in products throughout the planet, right? And Redis was part of this study. And what they discovered is out of those 48 critical failures, 92% of them, 92% could have been avoided with just better error handling. So I think Go has it right with the idea of error handling because it's going to lend itself and help with a lot more integrity. And we'll talk about error handling when we get into the design aspects of this video. But two great quotes here, one from JBD again, right? Failure is expected. Failure is not an odd case. Design systems to help you identify failure. Design systems that can recover from failure. This is going to be a big mantra that we have in this class throughout the video. And Kelsey Hightower, beautiful quote, product excellence. Product excellence is the difference between something that only works under certain conditions and something that only breaks under certain conditions. I mean, but I want to explain it. I want you to think about what Kelsey is saying here. These are engineering ideas, designs, and principles that we have to bring in with us day in and day out as we're writing code both at a micro level and architecturally at a macro level. All right, so that's integrity. We've got to take it seriously. If you don't take it seriously, I can tell you right now, you're not working for me. It's our #1 priority. And the funny thing about integrity is that it's not free. Like, nothing is free. And usually the cost of integrity is performance. We're going to lose a little bit of performance, maybe just nanoseconds of performance, but nothing is free. But we'll take that performance lost all day long if we have a system that's going to run solid day in and day out. So that's integrity. That's #1. When we're doing code reviews, when we're reading code in this video, we're going to make sure that everything has a high level of integrity first. Now, after integrity, our next priority is readability. And readability has different meanings depending upon the language and the systems. I mean, overall, we can say that readability means that we have to structure our systems to be more comprehensible. But that's kind of subjective, right? And readability actually has two aspects here. There's a subjective part to readability, and there is a measurable part of readability. The subjective part of readability really comes down to the idea that everybody on a team should be able to read code. We'll talk about that in a second. The other part of readability is that we do not hide the cost of code. We don't write code that hides the cost. And as an industry, we got into the habit of creating layers of generic abstraction which in the end of the day ends up hiding cost. And the worst thing that happens is we start building abstraction layers on top of our abstraction layers. We don't want to do that. Now, it's easy for me to say don't hide cost, but it's better if I can show you what I mean about not hiding cost. So I'm going to show you a little C++ code here. And this code is going to give us a good or better idea of what we mean by not hiding cost. And even though if you've never looked at C++ before, I promise you, you can read this code here. So if you look here in our C++ shell, lines 7 through 14 is the definition of a new type called foo. Now this is an object-oriented programming language, so foo has been defined with a constructor, a destructor, it's got a move constructor, a copy constructor, and it also has an operator, overload, for the assignment operator. These are things we don't have in Go. I mean, Go could be considered an object-oriented programming language. I don't consider it that. I've heard Rob Pike say it's a better object-oriented programming language. For me, it's a data-oriented language, and one of the reasons I say that is we don't have these features in the language like you have here in C++. So constructor, destructor, move, copy constructors, and our operator overload there. You see it all, there it is. Now on line 16, what we have is a function named f1. And what f1 is doing, this is constructing an object, this is object-oriented programming, an object of type foo, and then returning a copy of that object back out. So object's getting constructed on line 17, and then it returns right there. You can see on 16 the definition returning a copy of that object back out. So I've shown you 18 lines of code. You see it all there. And we get to line 23 and 27. This is where this code gets interesting. See on line 23, we're calling the f1 function. It's constructing, like we saw, that object there. It's returning a copy back out. We're declaring a variable of type foo named foo1. And then on line 27, we call f1 again, reassigning back to the foo1 variable. So I've now shown you 27 lines of code. There it is. It's all there in front of you. And here is my question, right? Looking at all of this code, when this program runs, the question is, how many objects of type foo get created? If and when do those constructors, destructors, those move and copy operators, assignment operators, when do all of that code behind the scenes get executed for line 23 and 27? You see, and if you don't ask me what version of C++ we're using, you're already wrong, because different versions of the C++ compiler are going to take different optimizations. This is what I mean by hiding code. When we look on line 23 or we look on line 27, we have absolutely no idea how this program is going to behave. We have no idea what code is going to execute behind these lines. This is hiding cost. Go doesn't have these constructors and destructors, doesn't have operator overloading, doesn't have these things because it hides cost. We want to be able to look at a line of code and predict reasonably well how that code's going to run, if it's even going to show up in a profiler or not. You can't do that with these features. Now, if I run this code here, you're going to see that for line 23, the compiler optimizes the copy away. So this time when we called f1, only one object is created or constructed, right? We see the constructor get called. But when we call f1 a second time on line 27, suddenly the object's constructed inside that function, a copy is returned back out, you start seeing all these other things happening. So think about it. The same function call in two different contexts created two different behaviors, two different costs. We cannot have code like this and then be able to maintain any mental model or any predictability on how this is going to run. All right, so this is what we mean about readability and not hiding cost. We don't want to hide the cost of things, and we're not going to do that in Go. But let's get back to the average developer. For me, the other part of readability is that the average developer on your team should have a full mental model of the code base, should know where everything is, should be able to debug it, should be able to program day in and day out and even teach that code base. The average developer should have a full mental model of your code base. And I want you to think about it. I mean, think about the team that you're working on right now. Ask yourself, am I the average developer on the products that we're working on? Do I have that full mental model of the code? Do I know where everything is? If there's a problem in production, can I debug it? If the answer is no, then I want you to say, am I less than the average developer? And if I am, what am I doing to become average? What are my teammates doing to become average? If I'm above average, am I helping the team maintain that level of average? Am I writing clever code that's really hurting the team? Like, that can be worse, right? And so I want you to always be evaluating yourself. Am I the average developer, and am I doing the things that are right to keep the average developer on my current team at a point where they can maintain those mental models and maintain maintainability, right, of the code base. And when you're hiring people, I need you to ask, are we hiring somebody that's average, less than average, more than average? Or what are we doing to our team dynamics here around readability? Look, you put me on a team building business-based web APIs, I'm above average. I've got to make sure that I'm writing code that's in line with the team. You put me on a crypto team, I'm below average, right? I've got to come up. They can't dummy down the code, but they also got to help me come up and be average. So these are the things we mean about readability. And moving forward, we're going to be talking about mental models. We're talking about readability at a team level. When we talk about not hiding cost, we're talking about writing code that we can predict reasonably well at that line, at that function. And have that level of comprehension, not hiding cost. Now, the last thing here on our code reviews will be simplicity. Actually, right before we even talk about simplicity, this is a great quote from Peter. I'm going to be bringing this quote up over and over again throughout the class. Making things easy to do is a false economy. Focus on making things easy to understand, and the rest will follow. This to me is huge. This is going to be embedded deep into everything we do. Don't make things easy to do. Make them easy to understand. And sometimes that means that we're going to have a little redundancy in a code base. Sometimes that means that things are going to be a little more tedious. But at the end of the day, it's not about your life when you're writing the code. It's about your life when the code is failing and you have to debug it. I want that to be our higher priority, right? So when the problems are occurring, we can reduce our stress levels by being able to maintain this code and fix it, as opposed to trying to reduce stress levels when we're trying to write it. All right? This has all got to be about again, handling the engineering problems when things are failing, not when things are good. Now, simplicity is last. And simplicity is last because it's something that you have to refactor into. You can't get to simplicity day one. And the funny thing is, simplicity is kind of fighting readability. If readability is about not hiding cost, simplicity is about hiding complexity. I'm now using the word hiding. We said don't hide. Well, simplicity is about hiding complexity without losing readability. So if you start hiding complexity in a generic way and with general abstractions, and we lose readability, you can't have it. And this is why simplicity is not something you achieve day one. You achieve it through refactoring. Look, you got to get something to work. Then we're going to do these code readability reviews. Once we've got code readability reviews in place and we feel like the code is comprehensible, now we can start asking questions about, well, how can we hide some of this complexity? This is a staged approach, right? And I hear people sometimes say, Bill, I don't have time to do this type of level of refactoring. Look, I'm telling you, you don't have time not to. Refactoring isn't something that you set a sprint for a week from now. It is something you're doing day in and day out. You get a piece of code working, we do code readability reviews, we clean up our comprehension of the code, we clean up our mental models of the code base, then we ask, how can we hide complexity without losing this readability? Now we can create some levels of decoupling. Now we can do these things. And it's a constant kind of flow of us doing this all day long. This is what we're going to get to. So as we now transition and to start looking at code, remember that our focus is going to be integrity first. And what's the cost of integrity? Some performance. Readability next. Being able to make sure that code is comprehensible, not just by us, also by our team, and that we're not hiding cost. And then third, we get into refactoring towards simplicity, about hiding complexity. This is our priorities all the time. And even as we go through the code base, these are going to be our priorities. I'm going to be bringing these things up over and over and over again. So now we're ready, our minds are framed, and we're ready to start looking at code.